Welcome again to Math Essentials Vector Calculus. We are with the curl, and this time we have summary and applications. So in the previous videos we have learned how to calculate the curl in the various coordinate systems, and curl is in short is nabla cross f. This is what we have reached in the end of the videos. Each video is either in Cartesian, cylindrical, or spherical. And today we will just learn. We even don't need to memorize all of this. We just need to memorize scaling factor, which we have learned a long ago. And as we know, for Cartesian, it's just 1, 1, 1. For cylindrical, 1, 1 for the lenses. And if we have angle, which is phi, it will be rho. And for spherical, again 1 for the r, it is a length, and for theta and phi it is just r and r sine theta. And then we need to memorize only one matrix which gather all of these coordinate systems. We just divide by 1 over h1, h2, h3, and put our vectors a1, a2, a3, put our derivative partial u1, partial u2, partial u3, put our vector f1, f2, f3, and finally first row and last row multiply each by h1, h2, h3. And if you just substitute what you can find here, I mean the scaling factor based on your coordinate system, you can simply restore the matrix in the various coordinate systems that we have learned. So now we move to some engineering and physics examples. Starting from the electromagnetism, we have one of the Maxwell equations, which is nabla cross E equal to minus partial by partial T of P. And the meaning of this equation is that if we have a time varying magnetic flux, this will give a rise to a circulating electric field. In fluid dynamics, we have a different quantity. We have the vorticity and the velocity. Again, the vorticity or the local spinning will cause a rise of the velocity or a circulating velocity. In thermodynamics, things are a little bit different. It depends on the condition. So if we have a pure conduction, we will have actually the heat flux, the curl of the heat flux, or nabla cross Q, will equal to 0. This means that heat flow has no rotation, it moves along the gradients. So let's wrap up what we have learned in this video. We have summarized the calculations of the curl in Cartesian, cylindrical, and spherical coordinates. Then we have generalized the curl calculation in the orthogonal curvilinear coordinate systems, because we have learned that once we know the general matrix and we know the scaling factors of this specific system, then we can write how the curl can be calculated. And finally, we have seen some engineering and physics example. And from next time, we will start to discuss theorems of vector calculus, including Green-Stokes and divergence or Gauss theorem, and link theorems to the divergence, gradient, and curl. Thank you.